And by my desktop device, it is now 10 a.m. in time for everybody's favorite chemist. I'm Richard Boyle. We've been doing this for a while now. We're about at midterms now. This is, I believe, the exact middle lecture. We've talked about chemistry, the periodic chart. We've talked about chemical reactions. We're going to talk about states of matter today. A lot of people will often ask, well, what's the matter? And I respond, nothing. What's the matter with you? Matter, if you recall, we defined as anything that has a mass and occupies a volume, occupies space. We started talking a little bit about the three states of matter last time. Now, there are more states of matter than just those three. But the three main states of matter, solid, liquid, gas. Solid, the molecules are kind of stuck in place, but they're not really stuck. I mean, they don't have translational freedom. They cannot move within their volume from one location to another. They're stuck in one location, but they do vibrate. They're not stationary. There's always motion in chemistry. The atoms, the molecules are rotating, they're vibrating, they're doing, no, not necessarily rotating. But there's always motion, even in solids, unless you're at absolute zero. And the only thing that we cannot reach absolute zero is a theoretical minimum temperature, much like the speed of light is a theoretical maximum velocity. We are very, very close to absolute zero, and there's some really strange effects that occur when you get down that cold. The only thing that's truly at absolute zero is my ex-wife's heart. Liquids have translational motion. Also, they slide over each other, and it's kind of a lot of freedom of motion, but only within a fixed volume. Gases have complete translational motion within their entire volume. In order to define a system, you need 4 parameters. We're going to open this one and accept that. You need 4 parameters in order to define a state. Only 4. We talked about one of them already, volume. Designated with a capital V. Volume is a region of space. That's all it really is. It's just a region of space. And remember, we talked about volume once before. Volume is an effect of the third dimension. Sorry, I'm a little bit off today. I'm not really feeling very well. I didn't get much sleep last night. I'm kind of in bad shape, but there it is. We're just define volume usually in cubics, cubic centimeter, cubic inch, which sometimes may sound odd, because if I have this volume here, this is not a cube. So when we say that something is, well, this is 500 milliliters, 500 milliliters is 500 cubic centimeters. Remember, 1 cubic centimeter, welcome back, Kim, is 1 milliliter. So even though a cubic centimeter is a tiny little cube, and this is not a cube, we talk about volume in terms of equivalence. It's the equivalent of 500 little 1 cubic centimeter cubes. The second parameter, Kim, we are talking about the 4 parameters we need to define a state. Volume is one of them. The second one is temperature. Very interesting history with temperature. Temperature was defined by early thermodynamicists as simply a measure of quantity of heat. And they didn't even know what heat was. Heat was what was transferred from a hot region of high temperature to a region of low temperature. They knew something was being transferred. They really had no idea what it was. Turns out heat is a measure of kinetic energy. The higher the temperature, the faster molecules and atoms will move. And much like tiny little billiard balls, if some of them start moving faster, they collide with the other ones and cause them to move faster as well, until eventually all of them in a volume is moving at the same, with the same average, let's say the same average kinetic energy, not necessarily the same average velocity, because kinetic energy is mass times velocity squared. So the heavier elements, the heavier molecules, will always move slower than the lighter, smaller ones, just because they have more mass. But they all have the same average. There are always fluctuations because we're talking an average here, but they will have the same average kinetic energy. This is actually how the microwave works. The radiation in microwaves excite the rotational speed, the rotational kinetic energy of water molecules. That's why some things do not heat up in the microwave. If you put styrofoam in the microwave and put it on high for 4 days, that styrofoam is going to sit there and laugh at you. It's not going to heat up at all because there's no water in it. What happens is you put something in there, you put your food in there. All food has water. Well, let's not say that. There are dehydrated things out there. But before we eat it, food has water in it. And what happens in the microwave, the radiation of the microwave causes the water molecules to rotate faster. As the water molecules rotate faster and collide with other nearby molecules, that rotational energy is converted into translational energy. They suddenly start moving faster and faster and faster until your food is appropriately warm. We talk about the amount of material. How much material is in there? How much gas? How much is there? N literally stands for moles. Moles. Remember, 1 mole is 6 times 6.02 times 10 to the 23rd, which reminds me, 10 days from now, National Mole Day. 6:02 in the morning until 6:02 in the evening on October 23rd. October 23rd, from 6:02 in the morning until 6:02 in the evening. National Mole Day. First time I ever heard of National Mole Day was on a poster in a fast food joint. I was kind of surprised, honestly. But how much we have factors into our state laws. Finally, we have pressure. Pushing down on me, pushing down on you. That's Queen's version of pressure. Pressure. Pressure is a unit of force. It is force per unit area. We're going to have a lot to say about pressure, but we're used to pressure. PSI. One of my tires, I think, has a slow leak in it. Every couple of weeks, every 2-3 weeks, I have to refill it because the pressure is low and my car goes just batty crazy if it gets down to 31 PSI. So your tire is low, blow it up. Oh, geez, 31, terrible. Usually we fill it to 35 PSI. 35 PSI. PSI stands for pounds per square inch. Force, pounds, not kilograms. Kilograms is mass, not pounds. Force is the pressure, is the amount it's how hard something is pressing against something else. If I weigh 160 pounds, that means that I am exerting 160 pounds of force on the earth. It's a force. Pounds is a force, not a mass. So it's force per unit area. In this case, the unit area is squared inches. Area, remember, is an effect of the second dimension. One dimension is length, two dimension area. Force per unit area. There are 4 parameters. These are 4 parameters, and actually doesn't have to be these 4 parameters. There are other parameters we can define that are kind of beyond the scope of this course. But these are the 4 principal parameters that we use to define the state of matter. Because of equations of state, any equation of state will be a function of all 4 of these. We're going to talk about one function of state in particular, the ideal gas law. And because we have 4 parameters here and they all have to fit into some given function of state, we have what we call, wow, am I going way beyond the scope of this course? We're going to go there anyway. We have 3 degrees of freedom. What that means is, with 3 degrees of freedom, I can define any 3 of these parameters to be anything that I want. But once I define those 3 parameters, the 4th one is fixed. That 4th parameter has one specific value to make the state law valid. So if we have 4 parameters that we can define, we always have 1 fewer degree of freedom. Okay. And we're going to talk about these. We're going to talk about the ideal gas law in a bit. Something keeps binging at me. But before we can discuss the ideal gas law, the first thing we have to discuss is an ideal gas. What is an ideal gas? Let's talk about that. An ideal gas is kind of like an ideal man. It's interesting to talk about, but it doesn't really exist. Okay, you don't have to laugh at that. Kim's not laughing. Okay, so anyway. An ideal gas is a model. It's a way for us to kind of understand molecular behavior. That's why we're looking at ideal gases. As we go through the properties of ideal gases, I will point out which ones are valid and which ones are not. Much like we talked about Dalton's atomic theory, we went through, and at each point, I would say this one is 100% accurate. This is very true. This one is mostly accurate, but has some problems. We're going to do the same thing with an ideal gas, the properties of an ideal gas. There are, just like with Dalton's atomic theory, there are 4 properties of ideal gases. Ideal gases are comprised of small indestructible particles. Ironically, this is the exact same way that Dalton's atomic theory started. So ideal gases are made of small, indestructible particles, just like Dalton's atomic theory. And of course, this is absolutely true. They're comprised of atoms or molecules or some combination of the two. The second assumption, all gas particles have zero volume. Gas particles have no volume. This is not true. This is not true. The truth is that the volume of our gas particles compared to the volume of the container are usually so small that they're negligible. Okay? Usually, the gas particle volume is negligible compared to the volume of the container. This is where the ideal gas law will sometimes fail, usually under very high pressures, which means you have a lot of gas particles compared to the volume. A lot of gas particles, they're compressed so tightly that their volume kind of matters. But I'm here in Nebraska. What's my volume? What's my area compared to the area of the state? If you were to parachute randomly into Nebraska, what are the odds that you're going to parachute where I am? Well, the odds are almost zero, because my area compared to the area of the state is negligible. The odds that you're actually going to hit me are approaching zero. That's what we mean when we say gas particles have zero volume. It just means that they're so small that, for all intents and purposes, they do not occupy a significant portion of the volume of the gas. The third assumption, the average, and I don't like using the word average, but we will. The average kinetic energy of the gas particles is directly proportional to its temperature. No, not its temperature. I apologize for that. I hope you have not put that in your notes yet. It is directly proportional to its absolute temperature. Its absolute temperature. All right. Let's unravel this. And this, by the way, absolutely true. So, my glasses. So far, number 2 is the only one that is an approximation that is not absolutely true, but is a very good approximation. The third one is absolutely true. The average kinetic energy. Remember, kinetic energy, according to physicists, is 1/2 mass times velocity squared. So we don't talk about velocity so much as we do kinetic energy. Mass times velocity squared. Can a VW bug push a semi? If you have a collision between a VW bug and a semi, which one is going to get moved? Well, most likely it's going to be the VW bug. The mass of the semi is so great compared to the mass of the VW bug that if there's a collision, that VW bug is getting pushed back in the direction of the semi. Unless that VW bug is moving so fast that its kinetic energy is significant enough to push back the semi. Is it possible? Yes. Is it as likely? No. Because it's velocity squared, which means it has to be moving really, really, really fast. But technically, it could. We see this on the gridiron in football when you have a massive defensive lineman and one of the other players who might be a lot smaller than that lineman is running towards him. If he runs and collides with that lineman hard enough, he's going to push that lineman on his butt. But he has to be moving really fast because the linemen are usually very large. It's all a question of kinetic energy. Which one has more kinetic energy? So when we say temperature, as temperature goes up, kinetic energy goes up. Yes, that does translate to velocity indirectly, because the velocity is also compared to the mass. Directly proportional. There are two kinds of proportionalities. Directly proportional means as one goes up, the other goes up. Inverse proportionality means as one goes up, the other goes down. All right? So, as you raise the temperature of something, its kinetic energy goes up. It's directly proportional. One goes up, the other goes up. If you add water to a bucket, its mass, its weight goes up. Direct proportionality. Inverse proportionality, one goes up, the other goes down. If you're if you're compressing a cylinder, like a bicycle, remember those old-fashioned bicycle pumps you used to pump up and down? If you put your finger on that hose, I don't know if you ever played this game. I used to play it all the time. Put your finger on the hose and try and compress that volume. As the pressure goes up, you're pressing harder and harder and harder. As the pressure goes up, the volume inside that cylinder goes down because you're pressing down the cylinder. It's inverse proportionality. Absolute temperature. Why is absolute so important? We're going to do a lot of calculations with these. Absolute temperature scales all begin at 0. The absolute temperature scale we're going to use in this course is Kelvin, but it is not the only absolute temperature scale out there. Kelvin corresponds to Celsius. Degrees Celsius, the temperature scale, and every temperature scale has a 0 point. It's where all kinetic energy comes to an end. That temperature on the Celsius scale is -273.9 0.15 degrees Celsius. Most people don't realize it actually goes beyond 273. It's 275.1499, trails off from there. So what do? We take our Celsius temperature and we add 273.15 to it. Why do we do that? Well, in calculations, if you're dividing by temperature and you happen to be dividing by 0 degrees Celsius, dividing by 0 is undefined. All of a sudden, your mathematical equation explodes and it comes up with nonsense. It makes no sense. So in our calculations, we must use an absolute temperature scale so that it never, ever, ever goes through 0. That's why we use the absolute temperature scale. So that's going to be really important when we start doing gas law calculations. The other temperature scale of which I'm aware, and there's an absolute temperature scale for every temperature scale that exists. The other temperature scale with which we are all familiar is Fahrenheit. Fahrenheit. The absolute temperature scale that corresponds to Fahrenheit is called Rankine. The Rankine temperature scale is the absolute temperature scale corresponding to Fahrenheit, just like Kelvin corresponds to Celsius. If I'm remembering correctly, and I may not be, absolute 0 in Fahrenheit is negative 453, if I'm not mistaken. So that's the Rankine scale. You take Fahrenheit and add 453, 454, whatever it is. I don't remember exactly. Then you have the Rankine absolute temperature scale. So part 3, all it really says is the higher the temperature, the higher the absolute temperature, the faster the molecules are going to be moving, or the higher the kinetic energy, to be more precise. So that one is absolutely true. And our fourth assumption. There are no intermolecular forces. Between gas particles. This is not true. It's a good assumption, but it is not true. In other words, there's no attraction and there's no repulsion between gas forces. In fact, there is. There has to be attractive forces, because that's what we're talking about here is potential energy. So number 3 is kinetic energy. Here we're talking about potential energy, 0 potential energy. We know these gas forces have potential energy. This is what holds gas particles together in their more condensed states. A condensed state is a solid or a liquid. Solids and liquids are called the condensed states. And it's the potential energy between particles that holds the molecules and atoms together in their condensed states. If there was no potential energy, there would be no liquids, there would be no solids. Okay? So we know there are potential energies. So why do we say there's none here? Well, in an ideal gas, we assume that the particles are so far apart. Remember the volume of these things is 0. We assume that they are so far apart that the potential energy is negligible. They're not feeling any potential energy, no attraction, no repulsion. My friend Mitch lives in Ohio. Kim, I'm going to ask an unfair question, and it's rhetorical, so do not answer this. But do you find my friend Mitch attractive? How can you? He's so far away, you can't see him. You can't say if he's really attractive or really repulsive. Probably shouldn't use the word repulsive, but there it is anyway. Because you can't see him, you don't know. And actually, it's worse than that. You've never spoken with the man. So, how do you know if you get along? You don't know. So, that's what's happening in gases. They're just so far apart that their volume is negligible and their intermolecular forces, their attraction is negligible. So, those are the four components of an ideal gas, unless you're Mick Jagger, in which case they are the components of an ideal gas. It's like a joke, it's just smaller. Okay. I used to teach the gas laws the way most textbooks do. Your textbook, no doubt, starts going into Boyle's law at this point, and Charles' law, or Chuck's law to his friends, and all of these different things. I had a student point out to me, you can derive, I want you to note what I just said here. I was teaching at the time, and a student pointed out to me that you can derive every gas law from the ideal gas law. So now I teach it backwards. Now I teach the ideal gas law first. Now, if you do that, you can derive Charles' law or Chuck's law to his friends. You can derive Boyle's law. You're not going to know the names. But I never cared about the names. If you know the laws, isn't that really what's most important? So I'm going to ask you to trust me, and then we're going to go and we're going to unravel this. Take these components and do a little bit of statistical thermodynamical magic to them, and you come up with the ideal gas law. As opposed to the ideal gas slaw, which is made from cabbage. It's like a joke. It's just smaller. The ideal gas law. And you should memorize this. You should memorize the ideal gas law. We've talked about all of these terms save one before. PV equals nRT. Pressure times volume is equal to the number of moles times a constant R times temperature. This constant R is the universal gas law constant. The universal gas law constant. Do I have it in my book? Kind of. The universal gas law constant has different values. 8.314, 0.08206. Well, if it has different values, how can it be a universal constant? And there are more that I do not know off the top of my head. Those don't look constant, do they? The secret is this, and I'm bringing this up for a very, very, very important point. The difference between these are units. They are the same. They are exactly the same, but they have different units. When you are performing gas law calculations, there are two cardinal rules. Never, never, never break a cardinal rule when you're doing these calculations. One, use consistent units. Always, always, always make sure that your units are consistent. The form of the ideal gas law that we're going to use in this chapter for gas laws is this one. I happen to know the other one, 8.314, because that's what we use in thermodynamics calculations. This universal gas law comes up more than once. But notice the units are given. Volume is given in liters, not milliliters, liters. Pressure is given in atmospheres, not PSI, not pascals, not kilopascals, atmospheres. The number of particles, always given in moles. And the temperature always uses the Kelvin temperature scale. Wow, am I having trouble with hiccups right now? So always use consistent units. Make sure that P is in liters because R is in liters. Make sure P is in atmospheres because R is in atmospheres. Make sure V is in liters because R is in liters, and so forth. Use consistent units. The second cardinal gas law, always, 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 always use an absolute temperature scale. Now, as I've said, there's more than one absolute temperature scale, but for the purposes of this course, we're only going to use Kelvin. Okay, for the purpose of this course, we will always use Kelvin. So I'm going to shorten it a little bit. To be more appropriately correct, you should say use an absolute temperature scale, but I'm going to say use Kelvin. I'm going to go one step further. Use an absolute temperature scale. Now, with the ideal gas law, PV equals nRT, we can derive every other relationship we need, and I'm going to show you how. But it's almost time for our break. So we're going to take a real quick break here. I will see you back here at 10:45. Thank you. I'll see you in a minute. All right. So we've talked about ideal gases, unless you're Mick Jagger, in which case they're gases. One of these days, you're going to have to look up that song, Jumpin' Jack Flash, to understand that joke. Because if you don't, I'm going to sit here and tell this joke repeatedly for the rest of the class, and you're not going to understand it. There's also a very fun movie with Whoopi Goldberg. Jumpin' Jack Flash, it's a gas. Anyway, we talked about ideal gases and what an ideal gas is, the properties of an ideal gas. We've talked about which ones are valid for real gases and which ones are not. And we've given you the ideal gas law. And I want you to, okay, here it is. Okay. Is this the only gas law that exists? No, of course not. There are, I know of off the top of my head, 2 additional gas laws that correct for these 2 shortcomings. Correct for the volume of gases and correct for the intermolecular forces. But the calculations using them become very algebraically complex very quickly, to the point where basically you can't even do it algebraically. You have to use a computer. And you get an answer pretty quickly, but it's not worth, for the small amount of correction, it's not worth it. And I want you to know what I just said. For the small amount of correction, it is not worth it. It turns out those assumptions, even the ones that are wrong, are so good that the ideal gas law gives you a wonderful approximation to your problem 99.99% of the time. It is almost always correct, certainly within the the kind of problems that you're likely to come across. But it is also kind of important to note that the ideal gas law fails because of those 2 assumptions. It fails under 2 extreme conditions. It fails under very high pressure. When I say very high pressure, I'm talking 100 atmospheres. I'm talking 100 times beyond what we feel every day. And since most of these calculations are going to be at 1 atmosphere of pressure or somewhere around there, the ideal gas law is fine. But under very high pressure, you're forcing the molecules to be really close together. And when they're really close together, the volume of the molecules begins to matter. So it does fail under very high pressure, and it also fails under very low temperature. I mean, well, when I say low temperature, I'm thinking approaching absolute zero. It doesn't really have to be. The reality is if the temperature is very near the condensation point, the temperature where you will either sublime or liquefy the gas, the ideal gas law may fail. There are 2 and only 2 types of energy in the world. You have kinetic energy, the energy of motion, and you have potential energy, the stored energy. What's really happening in an ideal gas law is we are saying that the kinetic energy is so high compared to the potential energy that the potential energy is negligible. As long as that's true, the ideal gas law is absolutely fine. Kim, you don't have to turn on your microphone and give me a thumbs up or thumbs down. Is there a child in your life, either your child, your niece, your nephew, a cousin, grandchild, a granddaughter, grandson, somewhere around toddler age? Oh, you're nodding. Okay, so you have a toddler in your life. Can you pick up your toddler? You can pick up your toddler, right? You pick that child up and hold the child. It's not that heavy. What if I were to give your toddler chocolate-covered espresso beans with sugar on top to make them even more palatable? Would you be able to pick up your toddler then? Probably not. What's happening? The potential energy is the same. The weight of the child is no different. But if they're on espresso beans and sugar, all of a sudden their kinetic energy is through the roof. You can try and pick them up, and it's like, you can't do it. The kinetic energy is too high. That's a gas. Kinetic energy is so much higher than potential energy that it doesn't matter how strong you are. You are not picking that child up. That's an ideal gas. Kinetic energy means the temperature is high enough that the kinetic energy compared to the potential energy just does not matter. At the other states, liquids, solids, the potential energy becomes much more important relative to the kinetic energy. Kinetic energy is always there, but remember, at lower temperatures, you have lower kinetic energy. So the potential energy, which is fixed, the potential energy, we're talking about what's called intermolecular forces. They don't change. They are fixed. They are your strength when you're trying to hold that child. Kinetic energies, they're fixed. They're always the same. The potential energy never changes, but the kinetic energy can vary wildly. Okay. Any questions about that? Kind of makes sense? All right. Well, that was weird. How'd I do that? Somehow I flipped the order of my pages. I did not do that intentionally. No, I didn't. No, that's fine. Okay. Remember I told you that I'm feeling a little bit tired and under the weather? I just thought I flipped my pages, but I did not. So how do you get the other gas laws out of the ideal gas? How do you do that? Let's remind ourselves of what the ideal gas law is. Many years ago, now I taught you the factor label method. The factor label method. And the factor label method helps you to solve most problems. Many years ago, but there are other techniques to problem solving, other approaches. Several years ago, one of the more popular techniques was called cross multiplication, which means if you have two parameters, A and B, you can always set up a ratio. And it will always give you the answer. Well, the problem is it will always give you an answer, but it will not necessarily give you a correct answer. For example, let's talk about Boyle's law. Boyle was looking at pressure-volume relationships. And he said, let's hold everything constant except for pressure and volume. Well, if we vary pressure and volume and hold the number of moles, of course, R is always a constant, and temperature, if we hold these three constant, then when we multiply them together, we're going to get a constant. We may not know what that constant is, but it does not change. If moles are fixed, if temperature is fixed, then pressure times volume is a constant. This is an example of where the cross multiplication problem solving technique would fail because we're not dividing pressure and volume. We're multiplying them. According to the ideal gas law, we have to. So if we have some given set of problems where we have an initial pressure and an initial volume, son, not, and we have a final pressure and we're trying to find a final volume, well, both of them are equal to the same constant. And if they're equal to the same constant, we don't need this in our equation. So Boyle's law comes down to this, which we derive straight from the periodic chart. Initial pressure times initial volume equals final pressure times final volume. Boyle's law. So for example, you want to do a quick calculation? So for example, suppose we have all right, we can do that. Suppose we have a Diet Coke bottle with a volume of 500 milliliters. With an initial volume of 500 milliliters. At atmospheric, well, let's say it's a little bit low pressure today. I think we have a low pressure zone coming in. So we're going to say 500 milliliters and our initial volume. Shoot. It's not pressure, that's volume. And our initial pressure (758 millimeters of mercury). Millimeters of mercury is one of the strangest sounding pressure units there is. Here's how they measure it. If you've ever seen an old-fashioned barometer, a barometer, the old-fashioned mercury barometers are just a tube closed on one end, the other end open in a pool of mercury. It is completely evacuated. That is to say, there's no gas in that tube. What happens is the higher the pressure, the higher the atmospheric pressure can press on that volume of mercury, but not in the tube. And as the pressure is pushing down on that mercury, it is pushing liquid up the tube. Atmospheric pressure is 760 millimeters of pressure. That means that at 1 atmosphere, that mercury will travel up that tube exactly 760 millimeters. 760 millimeters of mercury. That's how that's a pressure. I'm using it because it's a very unusual unit. I would like to know what is the volume if we increase the pressure to 1.03 atmospheres. All right. Let me copy this so we can put it to the next page. So we have an initial volume of 500 milliliters and an initial pressure of 758 millimeters of mercury. But then we take this bottle and we squeeze it so that the internal pressure is 1.03 atmospheres. What's the final volume? Well, remember the two cardinal rules. The second cardinal rule we can ignore because there's no temperature here. We don't have to worry about temperature. But the first cardinal rule, you must use consistent units. Now, if we keep our final volume at milliliters, we can use milliliters for our volume here. Notice that we're not using the ideal gas law constant R. If we were using R, we would have to convert milliliters to liters, but we're not. So we're going to leave it in milliliters. But our pressures are not consistent. We have millimeters of mercury here. We have atmospheres here. We cannot do this calculation without converting our pressure. There are many, many, many pressure units and conversion factors, honestly. So how do you do this? Well, it turns out if we look it up, we will discover that 1 atmosphere of pressure is 760 torr. And 1 torr is 1 millimeter of mercury. Somebody got tired of writing millimeter of mercury and said, oh, let's just call it a torr. So before we do anything else, we have to convert. I like working in atmospheres. So let's convert millimeters of mercury into atmosphere. So we're given 758 millimeters of mercury. Well, we know that 1 millimeter of mercury is 1 torr. Now we have torrs on the bottom. So we can put 706. Are you going to let me get away with this, Kim? I guess she is. This isn't going to work. Look, I have millimeters of mercury in the numerator. The next step, I need to cancel millimeters of mercury. I need to put it in the denominator, not the numerator. In this particular example, I would end up with the same thing because it's just a 1-to-1 ratio. Remember factor label. Each step, you want to cancel the unit. So now we have 1 atmosphere and 760 torr. So we grab our handy dandy calculator. This is a Hewlett-Packard calculator. The little label fell off many, many years ago. That little used to be a little thing there that said Hewlett-Packard and it gave the model number and everything. But that's okay. So if we do the calculation here, and if you have a calculator, I recommend playing along. We have 0.997 atmospheres of pressure. Now we have consistent units. We have atmospheres here. We have atmospheres here. Now, we've already derived Boyle's law. Now we just substitute. We have a new initial pressure, not a new one really, it's just different units. We know our initial volume is 500. We know our final pressure is 1.03. We are looking for our final volume. Now it becomes a matter of algebra, and how you do your algebra is unique to you. So I'm not going to show you, I'm not going to tell you how to do the algebra here. But basically, we're going to divide both sides by 1.03. I am going to rearrange it because I always like putting the unknown. And I want to show you something here while we're doing this. If you put your units down here, notice we have atmospheres in the numerator and atmospheres in the denominator. They will still cancel, and we are left with the units that we want. So we can still kind of use the factor label method here. When we get 484 to the correct number of significant figures, milliliters of gas. That's your Mick Jagger, in which case it's a gas. You haven't looked it up yet. That's why you don't get that joke. And we have just done our first ideal gas law calculation. So it happens to be Boyle's law, but it's a law. It works. Okay. Any questions about that example? Now, Boyle worked with pressure and volume. Along comes Charles. Worked with volume and temperature. Or Chuck's law to his friends. Chuck's law to his friends. Chuck's law is volume and temperature. So how do you get, there's that bing again. What keeps binging? It's driving me crazy. You know what? I'll bet it's a stupid thing. Let's close this. See, I told you. All right, I don't know if you could see what I just did or not, but let's get rid of that. Let's see if that helps. Charles law. Can you still see my Charles law up there? Okay. So again, we're going to start with the ideal gas law. In order to derive this, we want volume and temperature on the same side. So we're going to divide both of these sides by pressure to get rid of pressure on this side, and temperature to get rid of temperature on this side. And what are we left with? Volume over temperature. Volume over temperature is a constant. Now, once we see that the relationship, and here's the important thing. Relationship in Boyle says you multiply pressure times volume. When we do it here, we see that we divide volume divided by temperature. So Chuck's law, as his friends would call him, is a ratio. Here, the cross multiplication would work. But we have to derive these relationships through the ideal gas law. If you're starting to get how this works, you can see that we can derive any relationship that we want for these parameters, even if the law does not exist. We can still derive these relationships. Let's do a real quick calculation example. What did we end up with last time? Last time we ended up with 484 milliliters of gas. Let's use that same gas. Now, turns out we didn't squeeze the bottle. We put maybe a rubber band around it. We put a clamp on here that's holding the pressure constant. So we're not going to change the pressure now. We're going to keep the pressure constant. But this is at room temperature. So our initial temperature is room temperature. Thing. Oy vey. Find the final volume if we throw it in this freezer. Well, most freezers are at 0 degrees Celsius. So now we have our relationship. Our units are consistent. So we have 484 milliliters at 20 degrees Celsius. What's our final volume at 0 degrees Celsius? Our degrees Celsius cancel. Wait a minute, I did that wrong, didn't I? I did that wrong. No, I didn't. I did it right. And we got our final answer of 0 milliliters. That means that in our freezer, the gas disappears completely. Is that reasonable? Well, of course that's not reasonable. But remember, we have not one, but 2 cardinal rules. The first cardinal rule, make sure you have consistent units, which we have. The second cardinal rule we have violated because our temperature is not in an absolute scale. So before we can do this calculation, we must make sure that our temperature is in an absolute scale. To convert to Kelvin, just add 273.15 to our degrees Celsius. Now, we don't need the 0.15 because we don't have any decimal points after our temperatures. I'm going to assume that there's a decimal point here. And this will show you kind of a weird aspect of significant figures. Notice that our temperature, final temperature, is 1 sig Fig. But when working with significant figures, you always add to the point of the least significant. So our ones place, in both of these cases, our least significant digit is in the ones place. So we stop at 273. That means that our initial temperature is 293 Kelvin. Our final temperature is 273 Kelvin. And here's something very strange about significant figures. We have increased. When you add or subtract significant figures, you can change the number of significant figures in the final answer. So we have increased both of these significant figures to be 3 significant figures in our final answer. 0 degrees Celsius is 1 sig Fig. All of a sudden, it's 3. That's the way significant figures work. If you want to know more about why, you should consult a mathematician, because that has always blown my mind. But now we can use Chuck's law to his friends. Just substitute in, but use the absolute temperature scale. Did I do that last one correctly? I don't think I did. Yes, I did. I keep doubting myself. It's my day to doubt myself. Rearrange this a little bit. Notice again, the units Kelvin cancel. Picked up the wrong electronic device. And all of a sudden, we are down to 451 milliliters of gas at 1.03 atmospheres. These show 2 very important things. All calculations beyond this are the same. I can give you any set of parameters. I can give you 3 or 4 parameters, and you can derive the gas law relationship between them. But always, always, always make sure that your units are consistent and that you're using an absolute temperature scale. We're off and running to this chapter. Any questions before we go? Okay. This ends today because we are out of time. Don't be late to your next class, and I will talk to you on Tuesday.